Okay, so this lecture on chapter 7 is more about electron configuration and the periodic table and the intricacies about how different parts of the periodic table work. So we're going to start with how the periodic table kind of came to be, so to speak. Again, like I said, this is not a history class, but I think it's kind of interesting to understand the times we're talking about here. 1864, again, no running water, no electricity, no indoor plumbing, etc. People were still using outhouses. The Civil War hadn't even begun yet, and we were still exploring the West. So this is what's happening in the world of these newly developed chemists, previously all were physicists, figuring out and discovering all we know about elements that were being discovered at the time. And at the time, 1864, at this point, probably only about 5 or 6 elements were really discovered. Gold, silver, bronze, not bronze, bronze is an alloy, but elements, gold, silver, platinum, those were all in the know. And then carbon, nitrogen, oxygen, little bit of sulfur, so maybe a handful or two of elements were actually discovered at this point. Note, I say discover each time. There is no human that invented any of these, save for the last human designed ends of the periodic table that are just now have been coming into invention by man-made means. Everything back in the day were things that were discovered. So John Newlands, he noticed that if you arrange the elements in order of increasing atomic mass, every 8th element had similar properties. That's an important number, 8th element. He called them and referred to them as the octaves, or the octaves. There's this whole idea that when you get to an octet, where there's 8 electrons in the outermost shells, you have certain properties that are exhibited. So if you would put the elements in order of increasing atomic mass, every 8th element had the same properties. The problem is this didn't really work for anything past the second period in the periodic table, meaning calcium, because other things were going on with elements that hadn't even been discovered yet. But again, at the time, it's the only elements we really knew. So a couple years later, Dmitri Mendeleev, came in and said, you know what? We're going to come up with a better way of organizing these elements that we've discovered, the elements that we know exist. And we're finding that these elements that we know exist have regular, repeating, periodic properties. Okay? We refer to that as periodicity. Once Mendeleev had ordered the elements in also by way of atomic mass, increasing atomic mass, he learned, well, originally he said, you know what, no, this is going to work. We can do this with increasing atomic masses. But then there were some troubles he found. As more and more elements were being discovered, he realized there was issues with this. For example, argon and potassium, they would have had to switch places on the periodic table if it were done in order of increasing atomic mass. But potassium is very, very reactive. Potassium, K, based in the Latin name, that's its symbol, it's very reactive with water. In fact, you can go to YouTube and Google solid potassium in water and watch people put a small brick-sized piece of potassium and toss it into a lake, and the whole entire lake explodes. If you don't believe me, go to YouTube and Google it. Potassium is exorbitantly reactive. But argon is a noble gas, okay? When I was in undergrad in the 90s, we still referred to them as the inert gases, inert meaning non-reactive. And today, we can't call them non-reactive anymore because, for example, xenon, we can force into a reaction with fluorine, which is exceptionally reactive, for a very unstable short amount of time. So we can no longer call them inert gases because we know some of them can in fact react, but they react in such a way that it's very unstable and doesn't happen for a very long amount of time. So if we were to switch those positions on the periodic table, potassium would be put in the same grouping as unreactive neon and helium. That just doesn't work. So when we figure out periodicity, we've learned over time that it's the atomic number in order that needs to be considered. You'll notice that if you look on a periodic table, the number of the elements are in order, 1, 2, 3, 4, 5, 6, 7, all the way through 118 and then some. And what we have found is that it's not, we haven't given them an atomic number, the elements. We have not given the elements an atomic number because we want to put them in order of 1 through 100 and something. It's simply because putting them in that order gives us the most reasonable trends that occur down the families or the vertical up and down columns of reactivity and properties. When we talked about our main group elements, we talked about them having repeating familial patterns. And we also said that the transitional metals, the only thing regular and consistent and repeating patterns about those were that they were not consistent. So if you remember, the main group elements were groups 1 and 2, okay, the alkaline and alkali earth metals, and then groups 13 through 18, where the only specialty names here are the halogens, the noble gases, alkaline and alkaline earth metals. Then everything else were transitional. So these are your transitional metals, and these are your inner transitional metals. And the only thing regular and consistent about the transitionals is that they are not regular or consistent. They behave differently based on the environment in which they are reacted. So every single element has what we call valence electrons. These are the outermost electrons in the outermost shell of every single element. So again, if I start with my nucleus and I have these electron fixed energy levels that go out from the nucleus, if I were talking about this random one that I've drawn, I would say, okay, this valence this orbital here, this shell is my outermost shell, and any electrons that are contained in that outermost shell are my valence electrons. All the other electrons are the core electrons, and it's not that they're not important, it's not that they don't matter, it's just that for the most purposes of what we're talking about with chemistry, it's the valence electrons that do and are involved in the bonding of elements. So if I again look at the periodic table, what I can say is that all group 1 elements have 1 valence electron. All group 2, they have 2 valence electrons. If I look at sodium and I want to draw sodium, remember from last lecture, sodium's electron configuration is 1s2, 2s2p6, 3s1. Okay? So what that looks like is, here's my nucleus. The first S, which is 1s2, has 2 electrons. My next orbital is 2s2, and it has 2 electrons. The next one is p6. It's got a full p shell. So I'm going to say 1 pair, 2 pair, 3 pair. Keep in mind, each figure 8 has 2 electrons, but if I write the E's, it'll just start to become very messy. And then finally, my last sublevel is 3s1 with 1 electron. If you remember from the last couple of lectures that sodium, when it becomes an ion, is going to lose 1 electron. This is the electron that's going to go away. It's going to be lost to some non-metal. So if I'm going to get rid of that electron, what's left for electrons for sodium are 2 electrons from the 1s, 2 electrons from the 2s, and 6 electrons from the 2p. This right here now becomes its outermost electrons. Once I've gotten rid of the valence electron, the green valence electron is now gone. It's been given up. So what I'm left with are 8 total valence electrons after sodium becomes an ion. So sodium goes from regular sodium solid to a sodium ion plus 1 electron because that electron was lost. And actually, let me do this just to make it more clear. Okay, it loses that 1 electron that was in its valence shell. So what it's left with, it feels like and it behaves like it now has 8 electrons in its outermost shell. Its now new outermost shell. Those 8 electrons are what gives sodium ion an octet. Okay, 8 valence electrons in an element make it the most stable. Moving on, talking about valence electrons, group 13 has 3 valence electrons, 14, 4. Guess how many group 15 has? You guessed it, 5, 6, and then group 17 has 7, and the noble gases have 8. They already have an octet. They are happy. They are on their island with their Mai Tai, happy as can be, and that is why they are so unreactive. Now, when we talk about these core electrons and valence electrons, we have a couple of things going on with them. The first one is just a generic nuclear charge. We call that the capital letter Z. That is simply the number of protons in the nucleus of an atom. The effective nuclear charge, Z effect, is the magnitude of positive charge that is experienced by an electron. So if you can imagine that we have a nucleus with positive protons and electrons that orbit it, and I'm just making this up. This isn't really a real element. I'm just kind of making it up for the purposes of demonstration. Okay? If you can imagine that, for example, this electron right here, it is being pulled towards that positively charged nucleus because electrons are negative. However, this electron right here, the green electron, its pull towards the positively charged protons is shielded or kind of blocked by the yellow electron, by this electron right there. This is the Z effect. What is the actual magnitude of the pull of the protons in the nucleus by an electron that is shielded? As you move further and further away from the nucleus, the Z effect becomes more and more. The shielded electrons are more and more, they get interfered with by the core electrons. So the valence electrons, the ones all the way out in the valence shell here, they are shielded by all those core electrons. So when we talk about this effective nuclear charge, Z effect increases steadily from left to right across the period. So as we go left to right looking at the periodic table, the Z effect increases. If you just look, for example, from lithium to beryllium to boron to carbon to nitrogen, etc., you'll see that lithium has a much smaller Z effect than fluorine, which has a huge Z effect. Most of this is because fluorine has way more electrons than lithium, for example. So we can calculate the Z effect by Z minus sigma, where sigma is the shielding constant, and that is always a positive number, but always smaller than Z. And Z is, remember, the number of protons, and the sigma, again, is the number of the shielding constant, greater than 0, less than the number of protons. As we look from top to bottom of the periodic table, the Z effect is less significant, it's less important. We see less of a change because as we move from top to bottom of the periodic table, yes, the number of electrons increase, but as do the number of protons. So the difference between the number of protons versus electrons is a less difference than moving left to right. Atomic radius, this is the size of the radius from nucleus to edge of the element that decreases as we go up into the right of the periodic table. And the metallic character, or the rate at which something has more metal characteristics, also decreases as we go up into the right of the periodic table. When we talk about increasing atomic radius, we're talking about to the right and down of the periodic table. So, for example, fluorine has a teeny tiny radius where lithium is rather large. And if we also compare fluorine to, say, for example, cesium, you're going to see a huge difference there. I want you to go through these sample problems and really take a look at them and go through. I have also uploaded today, while I recorded this video, I also uploaded a periodicity worksheet. I highly recommend you go through it. It is very kind of long and in-depth. And no, it is for no credit or anything, but it will really help you understand the trends that go on within the periodic table. So there's a blank worksheet that's uploaded, and also the completely worked out with explanation key as to each answer. Ionization energy is the energy needed to remove an electron or to take an electron from something else. So if fluorine, for example, is going to take an electron from something else, keep in mind fluorine has a total of 7 valence electrons. It wants 8 electrons to form the octet. Therefore, generally fluorine will very easily and readily take 1 electron from something else in order to meet that octet. That's why when fluorine becomes an ion or gains an electron as a nonmetal, it has a -1 charge. That means it's picked up 1 electron to get that 8 valence electron octet. Okay, so ionization energy is the amount of energy needed to take an electron from something else. Sodium very easily gives up an electron. It's very easy. It's much easier for sodium to give up 1 electron, so its next lowest level of valence electrons has 8, rather than pick up 7 electrons. That's incredibly energetically difficult. If you look here, you can see just the general trends of the first ionization energy, meaning the energy needed to get 1 electron. There are also second, third, fourth, etc. ionization energies. We're not going to worry about those in this course. You just need to focus on the first ionization energy, or the energy needed to gain or to have an electron taken, the first electron taken from something. So if you look here, again, you don't have to memorize these numbers. You don't have to do anything with them. You just need to understand the concept. So for lithium to give up 1 electron, you're talking about an ionization energy in kilojoules per mole of 520. Where neon, for example, remember neon is in the halogens. It already has 8 valence electrons. Look at the difference here of the amount of energy it takes to pull or to take 1 electron from lithium versus 1 electron from neon. It's a huge difference. And the reason it's so huge is because neon is completely stable and happy with its 8 valence electrons, and it will hold on to those 8 valence electrons very tightly because it leads to stability. Stability of an element or a compound is the driving force in every behavior it has. I also want you to go through these sample problems. We are not going to do it. These are very straightforward, but you really need to understand the basic ionization energy concept. Electron affinity is the energy released when an atom in the gas phase accepts an electron. So here's the rule. When an element, atom, or compound accepts an electron, I don't know why Alexa just went off. I'm sorry about that. When one of these things accepts an electron, that means something is coming together. When something comes together, it is exothermic and energy is released. When I break apart something or break bonds, energy has to be input. So the electron affinity increases generically overall as we go up and to the right of our periodic table. That's a general trend. You can see these trends here when we compare, for example, fluorine, chlorine, bromine, and iodine. These are all in group 17. If we were to compare them with, for example, hydrogen, lithium, sodium, potassium, etc., which are all in group 1. You can see the electron affinity difference between the group 17 and the group 1, where you can see the increasing electron affinity as we move from left to right across the periodic table. Again, go through these sample problems in the PowerPoint. They're very straightforward. You need to understand it. So we already talked about metallic characteristic decreasing as we go up and to the right of the periodic table. Metals are very shiny, lustrous, malleable, very bendable. In fact, if I took a bar of solid gold, I could take my fingernail and carve my initials into it. That, solid gold is so soft, I can do that. This is why we have to add other metals to gold jewelry to make it hard enough in order to wear as jewelry, so we couldn't just bend it or pull it apart. Okay? Metals are great conductors of heat and electricity. They have low ionization energies. All metals form cations. We're not talking about metalloids. We're only talking about metals. They're going to form cations, meaning they will lose electrons and become positively charged. They form ionic compounds with nonmetals, and they form basic ionic compounds with oxygen. Nonmetals, on the other hand, will become negatively charged as anions because they will pick up electrons to get that octet. They're very brittle and chalky. I literally think of chalk when I think of nonmetals. I also think if you've ever been to a baseball field, that red clay, when it gets into big clumps and you can kind of just gently press into it and break it apart and just kind of falls apart in your hand, that's kind of the consistency of nonmetals. They are not malleable or bendable into whatever shape you want. They are terrible conductors of heat and electricity, and they form acidic molecular compounds with oxygen and have high electron affinities. That's why they form the anions. They pick up easily electrons to become negatively charged anions. So as we've already said, words are hard today, y'all. Metallic characteristic decreases as you go up and to the right. Metalloids, those are the ones, I call them the stair-step elements on the color-coded periodic table. Those are the ones that can really kind of fall to the metal or non-metal behaviors based on how they're reacted and the environment in which they are reacted. So I want you to go through this a little bit more through the main PowerPoint, the PowerPoints that I uploaded. We've talked about electronic configuration, and we talked about core notation and how to decide where which electron is in each main energy level and sublevel. Now we're going to talk about things that are isoelectronic. Elements that are isoelectronic, first and foremost, are either a noble gas and a cation or anion. And because they become a cation or anion, they gain or lose electrons and therefore have the electron configuration, the exact same electron configuration as a noble gas. So two things that have the same electron configuration are isoelectronic. For example, the electron configurations of sodium and the sodium cation are in front of you. What you see is that the neutral sodium has an electronic configuration of 1s2, 2s2, 2p6, 3s1. The sodium ion loses one electron, so the 3s1 electron, you'll notice, is gone. This sodium ion, if you look at your periodic table, is the exact same electron configuration of neon. This is why in our core notation, we can say neon 3s1 for neutral sodium. Once neutral sodium loses that 3s1, we're left with just neon. So neon and the sodium ion or sodium cation are isoelectronic. They have the same electron configuration. The same is true as chlorine. Here is neutral chlorine, and here is the chloride ion. Neutral chlorine, you'll note the P sublevel, which can hold a total of 6, only holds 5 electrons for neutral chlorine. It is missing one more electron to get to a full octet. As soon as it picks up an electron to have a full octet in its outermost shell, it now has the same electron configuration as argon. Here, as I've discussed, sodium ion is isoelectronic to neon, and chloride ion is isoelectronic to argon. Here are some more sample problems for you to go through. If you're looking at this, write the electron configurations for the following main group elements. So if I'm looking at nitrogen and I have my periodic table handy, I can do my little trick where each box is representative of an electron in nitrogen. So neutral nitrogen's electron configuration is 1s2, 2s2, p1, 2, 3. In nitrogen, if it's -3, that means it has gained 3 electrons. So now the 3 will be changed to 6 to show the 3 electrons that it gained. So N3 minus is now 1s2, 2s2, p6. D block elements, I'm not very concerned that you understand how and why they lose their valence electrons, but just understand, even if an electron is written first before something else, doesn't mean it's the outermost. It doesn't mean that it's going to be the one that is lost, or maybe it does. So what I mean by that is, here, remember, if you remember with transitional metals, 4s2 is written first before 3d6. And that's because the D sublevel is a higher energy than the S sublevel. So for these 2 electrons, for Fe2+, those are going to be lost first. We will not get argon 4s2, 3d4. That will not happen. These 4s2 electrons will be lost first because remember, the 4th main energy level, even though it is a lower level, it is still further out from the nucleus. So the further out from the nucleus, those are your valence electrons. Those are going to be the ones that are gone first. Here, if you just look at sodium, you need to understand that when sodium loses an electron, its atomic radius becomes smaller. And if we look here, if we compare lithium, it's kind of hard to tell from this, but what you're looking at here is the little gray part of lithium. That's the atomic radius when it's an ion. The purple half is how large the atomic radius is as a neutral, uncharged element. So when cations become cations and they lose electrons, they become smaller. When anions gain electrons, they become larger. And that should make sense because they're gaining or losing mass. Here are some more sample problems. If you were to put them in order of increasing radius, you are looking at what's happening. So these are all neutral. These are going to kind of be in the middle because they're neutral with their regular size. Potassium, hold on, let me fix that. Potassium is going to be smaller, generically speaking, and the ions are going to be larger, but you still have to maintain the trend, and the trend is decreasing atomic radius as you go up and to the right on the periodic table. So go ahead and work through these problems. Again, they're very straightforward and they're completely worked out combinations. One of the last relationships we have is the diagonal relationship. This is talking about relationships between elements that are diagonal from each other. Okay, and the reason they're similar in their behavior and their characteristics is because of charge densities. And we will get into charge densities of their cations later in the semester. Just know it exists. The next few slides, I'm not going to go over 100%. I don't expect you to memorize these. I just want you to understand the trends that are occurring. So for example, all of group 1 elements, they will all react with oxygen gas. Remember, oxygen gas is one of those 7 diatoms. Remember, the 7 diatoms are the elements that form the shape of a 7 on the periodic table, starting with nitrogen, and don't forget hydrogen. So they always occur naturally in nature in their letter or symbol 2 form. So all of the group 1 elements, those metals, will react with oxygen to form a metal oxide. We refer to these as metal oxides. The alkali metals, those are group 2. I'm sorry, I'm losing my mind right now. The alkali metals, again, group 1, can also form peroxides. Okay, you all have peroxide in your bathrooms, I'm assuming, and all that means is there's 2 oxygens present where we have some element, I'm just going to use E, where we get 2 oxygens bonded to each other, then whatever the element E is. This double oxygen, which is different from this one, means a peroxide. You will often see it abbreviated as ROOR, where R's are just some generic representation of the carbon group. Group 2 elements always form the +2 ions when they lose electrons. And in water, they form metal hydroxides. Okay, when group 2 metals are put in the presence of water, they form metal hydroxides. These are the metal hydroxides. And I know it's metal hydroxides because I'm really starting to learn and become familiar with the polyatomics, and hydroxide is one of those polyatomics. And hydrogen gas. Group 3 or 13 elements in the presence of oxygen will also form metal oxides. So here is your summary. Here are the trends of the summaries. As you go up and to the right of the periodic table, Z effect, ionization energy, effective nuclear charge, which is the effect, and electron affinity increase. Also, as you go up and to the right on the periodic table, the general trend is that atomic radii and metallic character decrease. You need to know well and understand these trends well, okay? Now, if you have a choice between looking at and comparing 2 elements left to right versus top and bottom, for example, if I asked you to compare fluorine and silicon, what's more important is looking left to right, not top to bottom. I highly, highly recommend. I can't tell you how much I highly recommend. You might see some of this on a test. Going through the Chapter 7 practice worksheet that I have of, the periodicity and the different trends. It is long, and I understand that. So maybe if you think you got a good grasp on this material, pick 1 or 2 questions from each section. And then the key is uploaded separately. And all of these practice worksheets that I've put up there that are just, useful information, helpful information, those are to help you prep for your test. So do go over those and do look at those. Any worksheet that I've uploaded that's just generic information, for example, the quantum number cheat sheet, all of those you can use on your test, unless it's something I've said, no, you really need to memorize this, okay? If you have any questions, feel free to shoot me an email or to post in the discussion forums, and I will see you next lecture.